Hi, my name is Itamar, and today I'll be talking about a best practices process for Docker packaging, and specifically in the context of Python applications running in production. So Docker packaging is fairly complicated, and the reasons are actually not because someone decided to make a complicated system, it's because this is just a very hard problem. And there's two basic reasons why it's so complicated. The first is history. Docker packaging of a Python application intersects 50 years of different technologies, all of which have to work together, all of which are connecting in this one place. So Unix was started in the 1970s, Linux builds on it, there's Python packaging, there's containers. And all of these technologies, all the design decisions they've made over the years, all of them have to interoperate. And so things like Unix signals, which were originally created in the 1970s, do actually impact your Docker packaging. And it's just something that Docker has to live with. And so all of these technologies, all this history in one place means a bunch of complexity. The other reason that packaging is complicated, and this is not Docker specific, it's just about packaging in general, is that packaging is at the intersection of a whole bunch of different organizational processes for software development. So if you have some application that you're running in production, you need to write the code, you need to test it, you need to deploy it. When it's running in production, you might want to catch errors, you have to do upgrades. All of these different processes interact and intersect with packaging, and packaging has to at least think a little bit about each of these. And so that's an additional source of complexity that you really can't get rid of. It's just inherent in the domain. And so as a result of all this complexity, you can't really go over all the best practices you need to know in one half-hour talk. I have a list of 70 best practices. I keep adding to them. And this is just for a very restricted domain, Python in production. And so what I can do instead is try to give you an overview, a big picture. In particular, when you're packaging your application for production, you need to do it within the limits of your work environment. So at any point, if you're at work, there might be a critical bug someone asks you to fix. One of your coworkers might need help. Some higher priority project will come around, and even if none of these things happen, you still have a limited amount of time to do packaging. There's plenty of other things you need to be doing. Again, there's a lot of best practices, and so you have to figure out which ones to do first, which ones to prioritize. And so what you need to do this well, and to do this within the time limits, is an iterative process where you start with the most important parts, and then each step builds on the previous steps. And then if you're interrupted, if halfway through the process you run out of time, at least you've done the most important things first. And you haven't done things in a way where critical parts of the packaging have been left to too late and now you can't do them. And the process I'm going to suggest is fairly generic. You might, in your particular domain, want to prioritize reproducibility, for example, and do it earlier on in the process. But this general order is good enough for most people. It's a good starting point. And it tries, as I said, to do the important parts of the packaging first. So it's easy to do a first pass of packaging your Docker, your Python application with Docker, and say, oh no, my image is gigantic. I'm going to spend a bunch of time making my image smaller. And it's reasonable to try to make your image smaller, but if you haven't thought about security, if you're shipping something that's less secure, then you may run out of time, and so you'll have a small image, but it's an insecure image, and that's not a good trade-off. And so you want to prioritize what best practices you implement so that you do the most important ones first. And ideally, you get to all of them, but if you run out of time, at least you have something that's been prioritized that is designed to be at least minimally usable. And so the rest of the talk, I'm going to be going through each of these steps in the process, getting something working, security, and so on, and explaining why you want to do that next, giving some examples, At the end of the talk, I will give links to some articles that I've written that go into much more details about all these best practices, cover many more best practices. Again, I can't cover all of them in a single talk. So the examples are just that, examples. They are not at all complete. There are many more things you should be doing, but I'm just trying to give you a flavor of the sort of things you need to be thinking about in each step and the kind of things that you have to get right in your packaging. So the first step when you're packaging an application is to get something working. If you cannot run your code from the Docker image, if you can't start up a container with your application, then the whole exercise is pointless. It doesn't matter if it's secure and fast and operationally lovely. If it's not running your application, then what's the point? And so this is an example Docker file. It's not a very good Docker file, but it might be enough to get your application running. So choose a base image, copy files in, install your code and dependencies, and then we say when you run this image to create a container, use the run server script. So something like that is sort of the basic you need to get something going. And in this context, there are best practices, but there are also BitMike requirements, because if you don't implement them, your container won't work. And so it's sort of a, you can think of it either way, but you do need to do them. So for example, when you are running a server inside your container, which is a common use case, you're running a web application like Django or Flask, you can listen on different interfaces. If you're testing on your regular computer, you may have been listening on 127.0.0.1, the loopback interface, localhost. And if you try to do that inside a container, when you can try to connect to your container, you'll get a connection refuse. It won't work. And the issue is that just like localhost on your computer is different than localhost on someone else's computer, and you can only talk to your own computer, not theirs, localhost inside a container is different than localhost on your host machine. So if you listen on localhost, listen 127.0.0.1, no one outside the container will be able to connect to your server. And so the solution is to listen on the 0.0.0.0 interface, which basically means all IP addresses that container or machine has, localhost and external. And once you do that, you'll be able to connect to it, assuming you've set up the correct forwarding. But if you listen on 127.0.0.1, port forwarding doesn't help you. You will never be able to connect to your application. So again, it's more of a requirement than a best practice, but it's a thing you need to do. So once you've reached the point where you can run your application at all, the next thing you might want to do is start running it somewhere that's not your local machine. And before you deploy anything publicly, it needs to be secure. So even if it's not being used by your clients or customers, even if it's just a test machine that's accessible to the internet, it's accessible to the internet. That means anyone on the internet, billions of people, can potentially reach it and attack it. And so if you want to be able to run your container outside the bounds of your personal computer, you need to spend some time making it secure. And so that's what we'll focus on next. That's the second step in the process. So here's an example of a security best practice. By default, when you take an image and run it, unless you've taken other steps or you tell it otherwise, the process inside the container will run as root. And it'll run inside a container. And so it's isolated in a variety of ways from the host machine. And so there are a bunch of constraints on it. But running as root does make your process more powerful than it needs to be, which means if an attacker takes over it, they'll have an easier time breaking out of the container. And again, there's ways your runtime environment can constrain this even more, but it's just good practice not to run as root. And so in this Docker file, what we're doing is we are creating a user, Linux user, called app user. We're telling the Docker file that from here on out we want to run as that user instead of as root. And then when we, for example, install our packages, they will run as the app user, not as root. When the image is started and the run server shell script is written, that will run as app user. And so if you do this, then anyone who gets your image and runs it will be running it as a non-root user, and it'll be just a bit more secure when people run it. Another thing you want to do when you're packaging your application is to install system package updates. So Docker provides on the Docker Hub a variety of base images, for example, the quote official Python Docker image, which I'm using in this case. These get updated on a fairly regular basis, but they don't always have the latest security updates included. And so this means that if you're using it as a base image, there might be a security update that you haven't gotten in like libc or OpenSSL or some other system library. And so it's good practice whenever you are creating a Docker file to run the appropriate commands to install system updates. In this case, we're using apt-get because this image is Debian based. If it was a Red Hat based image, you would do dnf command. But either way, you want to be installing security updates because you can't rely on the base image having it in all cases. And so in the examples we've given so far, they've basically involved editing your Docker file. And so more broadly, changing the artifacts that you use to package your application. The startup scripts, the build scripts, Docker file, and so on. And these sort of, this part of the packaging is sort of a one-off thing. You might tweak it occasionally, but in general, you write it once, you get everything working, and then you don't have to think about it very much. But packaging isn't just about these configuration files. It's not just a one-off thing. Packaging also requires you to have ongoing processes, things that you will continue to do so long as you are running your application. You can't just do them once and then forget about them. And security updates are sort of a critical and very important example of an ongoing process you need. When you create a Docker image, it's an immutable artifact. You can't change it. And that has a bunch of benefits, but it also has a downside, which is every time there's a security update, you have to create a new image. And you have to take that image and make sure you deploy it if you have if you run these in as an ongoing basis, like a container running a web application. You have to redeploy it with a new image, or the security updates don't help you. And so that means is you need an ongoing process that tells you about security updates, updates those dependencies, which might require changes to configuration files. Maybe not. You just have to rebuild the image. To rebuild the image, you have to redeploy application if relevant. For batch jobs, you don't have to do so. For web applications, you would. And so the end result is you can't stop thinking about security when you're done with the first pass of packaging. You need to set up an ongoing organizational process that will deal with it. So we talked about two steps in the packaging process, just getting something working and then security. And now that you have a secure image, it's time to do some more automation of how images are built. You want to start maybe running this in production. You don't want to have to manually run the builds for each images. That's error prone. You might have other people in your team who want to build images. You want things to just automatically build the image. Maybe you want to automatically deploy them. And so the next step is to integrate image building into your automated build system. So GitLab CI, Circle CI, GitHub Actions, Jenkins, whatever. You want to build your images automatically. And so down here, there's an example script, the sort of simplest possible automated build script, which basically runs some tests, builds the image, and then pushes it to an image registry. And it's a bash script, so I'm doing the magic set -euo pipe fail line you should put at the top of every shell script to make it actually stop when there's errors and not just keep going silently. And so that's sort of the minimal thing you need, but there are other best practices you can apply along the way. When you do this, you need to think about how your automated build integrates with the development process. The way your team writes code, the way your team deploys code. For example, are you going to run tests before you do the packaging? Are you going to use the resulting Docker image for some sort of integration test? Are you going to do both? How do you deal with branches? We'll talk about that. Is packaging going to be a bottleneck? If building your Docker images takes an hour, then this is going to be a problem for your developers. And maybe you want to prioritize speeding up your builds. So you have to think about how all these things integrate with your existing processes. So here's an example of a best practice you can run as part of your automated builds. Run security scanners. Ideally, you're being notified of security updates proactively, but it's good to have security scans for dependencies just as a belt and suspender sort of thing. So trivy, for example, is a tool that can scan both your Python dependencies and system packages for known security issues. So it'll say something like OpenSSL on this Docker image has a security vulnerability, or Django has a new release that fixes security vulnerability, that sort of thing. You can also have problems in your own code, and these sort of security scanners will never find them. There's other tools, like for example Bandit, that will scan your code for patterns of code that look like a vulnerability. So maybe you can catch a SQL injection that you have in your code by mistake. And so it's just good practice to have, and it makes your code more secure. We talked about how packaging interacts with branches. So it's fairly common to have feature development happen on a branch. So you have branch 1, 2, 3. So you for ticket 1, 2, 3, and you're building that code, adding code there, and then you open a pull request. And then that pull request, you want to automatically build a Docker image, maybe for integration testing, maybe for manual testing. When you build and push that image, you don't want it to overwrite the image you use for production. So if you just always push your image with the same name, then images from your branches will trash images from your main branch, and that means you might accidentally deploy to production an image that was built on an in-progress broken branch. So one way you can deal with that is by naming your Docker images based on the Git branch. So here we figure out the Git branch using this little command I got from Stack Overflow, and then we build the image, we give it the part after the colon, the tag, is based on the branch, and then we push using that name. So for example, your main branch will be your image :main, and the 1, 2, 3 more cowbell branch will be your image: 1, 2, 3 more cowbell. And so you can get images that are named based on Git branches and they don't stomp on each other. So at this point, we have an image that runs, that is more or less secure. We've automated builds. And so now we're hopefully running things in production. We want it to run well there. We want it to start up quickly. We want it to shut down quickly. We want the ability to debug things because it's running now. And so we want to be able to figure out errors. We want to figure out where an image came from. And so this is sort of a grab bag of various things you need to run and operate your images and containers more easily and just make things easier to debug. So for example, when you have a bug in your Python code which causes an error, it'll throw an exception. If that exception isn't handled, you'll have a traceback. The traceback will get logged. And so you can look through your logs or maybe some sort of service that tracks errors and say, oh, I got this traceback. There's a bug. This will help me figure out where the bug is from. If you have a bug in C code, you may well just get a segfault. So your program will just crash silently. There will be no logs. And it'll be much more difficult to figure out what caused it. You might be using a whole bunch of different libraries with low-level C code. You won't know which one caused the problem. It's a problem. However, Python has a built-in feature called fault handler that will automatically log Python tracebacks on segfaults. It doesn't really have any performance overhead, so you should really always just enable it. The way you set it is by adding an environment variable called Python fault handler and setting that to 1. So here we're doing it in our Docker file. And if you do that, then if you have a crash in your C code that causes a segfault, you'll get a nice Python traceback. And you can say, oh, it was this library that caused the problem, and I was calling this function. That makes it much easier to figure out how to fix it. So we talked earlier about naming your images based on the Git branch. And that's great for making sure images don't stop on each other. But image names, their tags, don't actually get embedded in the image itself. And so if you are looking at an image that's already running, you may not be able to figure out what Git commit it came from. Even if you have a tag which is my image name : the hash of the Git commit, you still, if you ran it as my image : main, that information about the Git commit is gone. It's not there anymore because the tag is not in the image itself. But Docker has a feature called labels that lets you embed metadata into the image. It'll always be there, and then you can use the inspect command to look at it. And so when you create your Docker images, it's good practice to label them with a current commit and git branch of the code that you use to generate the image, and that way you can figure out where exactly this image came from, what exact code is packaged inside of it. So you have an image that runs, it's secure, it's built automatically, it runs well in production. So now we have to start worrying about the passage of time. This week, the major dependencies you depend on probably won't change dramatically. If you use pandas, probably there won't be a new release of pandas this week. Python is definitely not having a major new release this week. Matplotlib, whatever. Most libraries, most applications you depend on won't change that much over the course of a few days. In 6 months, there will be some major release, probably just one of the libraries you depend on. 2 years from now, when your application might still be running, most of your dependencies will have changed. We will have new major releases. And so in order to deal with that, you want reproducible builds where you can update your dependencies in a controlled manner. And reproducibility is a process. You can't just stop updating your software. At the same time, you can't just always install the latest version. So if you always install the latest version of your Python dependencies every time you rebuild your Docker image, there's no reproducibility. Today you might be using one version of Django, tomorrow you might be using a different Django, they might be backwards incompatible, now your web application breaks, even though you haven't changed your code. It's not good. So what you want to do is you want to pin all your dependencies, freeze them to particular versions, so you always get the same version of Django, the same version of pandas installed. If you then don't change these dependencies, if you always install the same version of Django, then now you start having to worry about not getting bug fixes or security updates. So for example, Django has a long-term support version, so at least they will give you bug fixes, but in April 2022, so a few weeks, they will stop support for 2.2. So if you're using Django 2.2, you are not going to get any security updates for it starting in April or May. And so that's a problem. You do need to upgrade over time. So you need an organizational process to update your Python dependencies on a regular basis, while at the same time, in the short term, every rebuild should use the exact same version of all your dependencies. For your system packages, for the Linux distribution that their image is built on, you'll want some operating system that has security updates, but also gives you backwards compatibility. So Ubuntu long-term support releases, Debian Stable, Red Hat Enterprise Linux, one of the Red Hat clones like Oracle or Rocky Linux or Alma Linux. All of these will provide backwards compatibility with security updates. The quote official Python images provided on the Docker Hub are based on Debian Stable, but they give you access to newer versions of Python, so they're a nice image to use if you need a specific version of Python. So for example, Python 3.10/slim/bullseye is Python 3.10, the latest point release. Debian 11, which is the latest stable version, codename Bullseye. They name Debian releases after characters from Toy Story. And the slim means the small version of the image, so it takes up less space. Your Python dependencies, as I said, you want to pin to specific versions. And there's tools like pipenv or poetry that do this for you. But the easiest one to use is a tool called pip-tools. Comes, well, a bunch of ways to do this, but basically it'll take something like a requirements.in file that looks like Django and turns it into requirements.text with specific versions of Django, but also specific versions of all of Django's dependencies and its dependencies. So every single library that gets imported, either by you or by the code you import, gets pinned to a specific version, and so you have a reproducible build. But again, you need an ongoing process to regenerate this file over time so that you can get security updates. You can't just do this once and then forget about it. So at this point, we've gotten all the way from a working image to one with security, automated builds, runs well, it's reproducible, and so in some sense we're done. However, if you have a really slow build, if you have a really gigantic image, these things can get expensive. Like if your whole team's waiting 20 minutes on every pull request for a Docker image to build, that's a waste of time, cost money. And so at this point, we want to optimize your build, optimize your image, make it faster, build faster, make the images smaller if necessary. So here's one way to make your image build faster. Don't use Alpine Linux. And this is something of a Python-specific issue. When you install a package from pip-tools, you often get a precompiled binary package, so you don't have to compile it yourself. However, Alpine Linux, for technical details, can't actually use most precompiled builds from pip-tools. So that means is you will have to recompile them from scratch. And so, for example, just installing pandas and matplotlib will take 30 seconds if you just do it on a Debian-based image. So this is a test I did a while ago, so it's using Debian, the old version of Debian Stable, Buster. So if you just install those packages on my computer, it's 30 seconds because it just has to download them. If you install an Alpine, it was 1,500 seconds, 50 times slower. Just a huge amount of time because you had to compile matplotlib and pandas and all their dependencies from scratch. The situation is improving. People are starting to provide wheels that work with Alpine, but in general, I would just suggest avoiding Alpine. It doesn't buy you very much in terms of image size, and it will make your packaging run much, much slower. As an example of best practice for making your images smaller, when you do a pip install, by default, pip will keep a copy of a downloaded package on disk. In case you have created a new virtual env and want to install the same package, you won't have to download it again. And so for development, that's great. For a Docker image, that's just a waste of disk space because you're not going to create a new virtual env inside your Docker image typically. And so you can use the -- no cache dir option to say, don't bother keeping copies of these packages when you download them, which means you'll have a smaller image and it otherwise won't affect your image at all. So that's our process. Again, your particular application, you might do it in a different order. If you do this every day, you'll just end up doing these steps just automatically as you go, and so you won't have to think about the process anymore. But as a starting point, this order, getting something working, security, automated builds, running well in production, reproducibility, and optimization is a good order for you to package your application. And it will help you prioritize important things like security. So if you run out of time, you'll have at least have a secure image. And one thing I've talked about earlier, but I want to reemphasize, packaging isn't just about artifacts. It isn't just about configuration files. It's not just about writing a good Docker file or a good build script. Packaging is something that interacts with your development processes, like coding, deployment, upgrades. And it's also something that requires ongoing processes. You need an ongoing process for security updates. You need an ongoing process for dealing with dependency updates, like going from across major versions of Django, or testing a new version of pandas. You need to think about packaging not as a thing that ends after the first day when you write the config files, but a thing that needs you to think about how it's going to change over time and how you're going to keep it up to date over time. So that's my talk. If you go to my website, pythonspeed.com, I have a prose version of this talk that doesn't have the examples, but explains the process and sort of talks you through it in more detail. And I have at pythonspeed.com/docker a huge number of articles about best practices for packaging Python applications with Docker for production. And so if you want to learn more about the best practice examples I gave in this talk in much more detail, I encourage you to go check out these articles. And thank you very much.